tonight, we step away from the Earth, away from cities, kingdoms, and the rise and fall of human history, and drift into a silence so vast that even time begins to feel different. For centuries, people looked up at the night sky and imagined that with enough patience, enough mathematics, and enough powerful instruments, the universe could eventually be mapped like an empire on parchment. It would be immense, yes, but still measurable, still graspable, still something the human mind could hold. But then the James Webb Space Telescope opened its golden eye toward regions of darkness that appeared almost empty, and what it found was not emptiness at all. It found ancient galaxies where none were expected, brilliant structures forming far too early, and light that had been traveling toward us since long before the Earth existed. It revealed that the universe is not only larger than we once believed, but stranger, older in appearance, and far more hidden than our instincts allow us to imagine. So tonight, as the world grows quiet around you, let us follow that ancient light to the farthest edge of what can be known, and gently consider a truth both beautiful and unsettling, that most of reality may forever remain beyond our reach. To understand what the James Webb Space Telescope is truly revealing, we first have to let go of one comforting illusion. The sky above us does not show the universe as it is now. It shows the universe as it was. That may sound simple at first, almost obvious, but the deeper you follow the idea, the stranger it becomes. Light does not arrive instantly. It travels at the fastest speed nature allows, and yet even that speed is finite. So whenever we see anything at all, whether it is a candle across a room, the moon above the horizon, or a distant galaxy suspended in darkness, we are seeing something from the past. The farther away it is, the older the image becomes by the time it reaches us. In daily life, these delays are too small to matter. A mountain across the landscape appears present. The face of another person seems immediate. Our minds were not built to notice such tiny lags, but the universe operates on scales so immense that delay becomes destiny. The moon appears as it was a little over a second ago. The sun, as it was about 8 minutes ago. The nearest star beyond our sun appears as it was more than 4 years in the past. And when we look toward distant galaxies, we are no longer seeing years or centuries ago, but billions of years ago. This means the night sky is not a live scene. It is an archive, a vast museum of delayed messages, each photon carrying a timestamp from a different era of cosmic history. Some of the light entering our telescopes tonight began its journey before the Earth had oceans, before the sun existed, before our galaxy had fully taken shape. The heavens do not merely surround us in space, they surround us in time. And yet, those messages do not remain unchanged. As the universe expands, space itself stretches, and the light crossing it stretches too. Waves of blue and visible light lengthen into red, then farther into infrared. This redshift is more than a color shift. It is a record of how much the universe has expanded while that light was in transit. That is why James Webb matters so deeply. Earlier telescopes, powerful as they were, could only see part of the story. Webb was built to follow the ancient light after it slipped beyond visible sight, to catch the faint infrared whispers of galaxies so distant that their original glow had been stretched nearly into invisibility. It was designed not simply to look farther, but to listen more carefully to the oldest surviving messages in existence. The James Webb Space Telescope is often described as a more powerful successor to Hubble, but that comparison hides just how different it truly is. Webb was not built merely to sharpen old views. It was built to see a universe that had, until now, been hidden from us. Its great mirror stretches more than 21 feet across, made of 18 hexagonal segments working together like a single golden eye. That gold is not decoration. It was chosen because it reflects infrared light with remarkable efficiency. And infrared is the key to everything Webb was sent to find. The oldest galaxies in the universe do not shine toward us in the same way they once did. Their light has been stretched by cosmic expansion, pulled out of the visible range and into the infrared. To study the earliest chapters of cosmic history, Webb had to become an infrared telescope of extraordinary sensitivity. But that created a problem. Infrared light is closely bound to heat. Anything warm gives it off. A telescope heated by sunlight, by electronics, or even by its own structure would glow with false signals and drown out the faint, ancient light it was trying to detect. To see the first galaxies, Webb had to become unimaginably cold. That is why it does not orbit close to Earth like Hubble. Instead, Webb operates nearly 1 million miles away, near a gravitational balance point called L2. There, it can keep the Sun, Earth, and Moon on the same side, while a vast layered sun shield blocks their warmth. This shield, thin as foil and spread like a giant silver sail, allows the telescope's observing side to cool to temperatures so low that it can detect light arriving from the edge of the observable universe. In a sense, Webb had to be silenced before it could listen. It had to remove its own thermal noise, its own glowing interference, until it became quiet enough to hear the universe whisper. And that whisper is astonishingly old. When Webb stares into a patch of sky that looks empty to human eyes, it is not staring into nothing. It is waiting patiently, sometimes for hours, sometimes for days, collecting photons that have crossed almost the entire observable cosmos. These are not bright streams of light rushing in all at once. They are sparse arrivals, ancient messengers appearing one by one from epochs so distant that the events they describe happened before our world was born. This is what makes Webb feel almost philosophical as much as scientific. It reminds us that seeing is not simple. Observation is an encounter with delay, with distance, with the fragile survival of information across time. And when Webb gathers enough of that ancient light to form an image, it does not show us the universe in its current state. It shows us a preserved moment from a reality long gone, a fragment of cosmic history still traveling toward us through the dark. For much of modern astronomy, the early universe was imagined as a dim and cautious place. After the Big Bang, matter was spread thinly through expanding space. Gravity, though relentless, was expected to need time. Gas would cool slowly. Dark matter halos would gather mass gradually. The first stars would flicker into existence in scattered pockets. And only after long ages would those small beginnings grow into true galaxies. The universe, in this older picture, learned to walk before it learned to run. But when James Webb began looking back toward cosmic dawn, that expectation started to unravel. Instead of finding only faint, fragile structures, it found brightness, again and again, in regions of time where astronomers had expected scarcity. Webb detected galaxies already shining with startling intensity. These were not weak little smudges barely announcing their presence. Some were already massive, already crowded with stars, already burning through gas at astonishing rates. This was deeply unsettling, because brightness in astronomy is not just beauty, it is evidence. A bright galaxy implies large numbers of stars, and stars do more than illuminate darkness. In their cores, they build heavier elements such as carbon, oxygen, and nitrogen. Those elements are then cast outward when stars die, enriching the gas from which later generations of stars and planets may form. So when Webb detects chemically mature galaxies at such early times, it suggests that not one generation of stars had formed, but several. The process of creation and destruction had already been repeated, and far sooner than many theories allowed. To imagine the strangeness of this, think of arriving at what should be the foundation of a city, expecting bare ground, rough stones, and perhaps the outlines of roads. Instead, you find towers already standing, furnaces already burning, and signs of entire neighborhoods that have lived and changed before your arrival. That is what these early galaxies felt like to astronomers. They were not foundations. They were already thriving. Some researchers even nicknamed a few of these objects universe breakers, not because they literally shattered cosmology, but because they seemed to violate the timetable that standard models had long implied. Later analysis softened the most extreme interpretations. Some galaxies may appear brighter because active black holes contribute to their glow. Some masses may have been overestimated in the earliest excitement. But even after corrections, the deeper problem remained. The early universe was still brighter, busier, and more developed than expected. It had not emerged gently into complexity. It had rushed toward it. As surprising as those early galaxies were, Webb uncovered something perhaps even more difficult to explain. In the hearts of some of these young systems, astronomers found evidence of enormous black holes already in place when the universe was less than 500 million years old, and not merely modest black holes born from single stars, but monsters with masses reaching millions or even billions of suns. That presents a serious problem. Under ordinary expectations, black holes begin small. A massive star lives its life, collapses, and leaves behind a black hole perhaps tens of times heavier than the Sun. From there, growth is possible, but not unlimited. Matter falling inward becomes hot and radiant, and that radiation pushes outward, slowing the inflow. Even under favorable conditions, building a supermassive black hole should take immense time. Yet Webb keeps finding signs that some of them were already present astonishingly early. It is as though the universe not only built cities ahead of schedule, but somehow raised vast fortresses in their centers before the roads were finished. To explain this, astronomers have been forced to entertain possibilities once considered rather extreme. Perhaps some black holes did not begin as the remains of stars at all, but formed by the direct collapse of giant clouds of gas. Perhaps the first stars were far larger than those common today, so massive that when they died, they left behind unusually heavy seeds. Perhaps the dense conditions of the early universe encouraged repeated mergers, allowing black holes to combine and grow far more quickly than once assumed. None of these ideas has yet claimed victory. Each solves part of the mystery and leaves other questions behind. That uncertainty is what makes this moment in cosmology so fascinating. Webb is not merely filling in missing details of a familiar story. It is forcing scientists to ask whether the opening chapters of the universe were written according to rules, more efficient, more violent, or simply more unfamiliar than we imagined. There is also something haunting in this discovery. These black holes are not visible in the usual sense. We know them by their effects, by the furious energy released as matter spirals inward, by the strange brightness surrounding an object that itself emits nothing. In the young universe, while galaxies were still assembling and the first heavy elements were being forged, these invisible engines were already feeding in darkness. And that leads us to an even larger question. If stars, galaxies, and black holes all form so quickly, then perhaps the universe has always been more crowded than we once believed, And when Webb began to count what was really out there, that suspicion only deepened. For most of the 20th century, astronomers believed they had reached a reasonable answer to one of the largest questions the human mind can ask. How many galaxies exist in the universe? The method was elegant in principle. Point a telescope toward a tiny patch of sky that appears empty, count every galaxy visible there, and then scale that number up across the rest of the heavens. When the Hubble Space Telescope performed its famous deep field observations, the results were breathtaking. In a region of sky so small it could be covered by a grain of sand held at arm's length, thousands of galaxies appeared. What had looked like darkness was suddenly revealed as a crowded field of distant systems, each one containing stars, gas, dust, and perhaps worlds of its own. From those observations, astronomers estimated that the observable universe might contain a few 100 billion galaxies. The number was so vast that it felt almost beyond revision. Then James Webb looked into that same darkness. Where Hubble had seen black gaps, Webb found faint infrared glows. Where earlier images had suggested emptiness, Webb revealed hidden structure. This was not because Hubble had failed. It was because the oldest and most distant galaxies had slipped beyond visible light. Their light had stretched with cosmic expansion, moving into infrared wavelengths that Hubble could not fully capture. They had been there all along, waiting in frequencies our eyes and instruments had only partly learned to hear. And when Webb listened, the silence became crowded. In one extraordinary survey, Webb examined a region of sky only slightly larger than a few full moons placed side by side. After collecting immense amounts of data, astronomers found hundreds of thousands of galaxies filling that small patch alone. Not stars within our own galaxy, but entire galaxies, each one a vast island of matter with its own history, its own stars, and perhaps its own planetary systems circling in darkness. This changes more than a number. It changes atmosphere. The universe no longer feels like a sparse arrangement of isolated lights in a mostly empty void. It begins to feel layered, thick with structure, rich in hidden abundance. Darkness itself starts to seem misleading. Much of what we call empty space is not truly empty at all. It is simply too distant, too ancient, or too faint for ordinary sight. And there is something deeply humbling in that. Human beings once looked at the sky and imagined the stars as a few bright lanterns fixed in a manageable dome. Now we know that even a tiny patch of blackness contains histories beyond counting. Webb did not merely reveal more objects. It revealed that our previous sense of cosmic scale was still, in some ways, provincial. The heavens are not only larger than we thought, they are more crowded than we ever felt. As astronomers began to examine Webb's flood of distant galaxies more carefully, another realization emerged. The universe is not arranged randomly. Galaxies are not scattered through space like loose grains of sand tossed into darkness. They gather, they align, they trace patterns so large that once seen, they begin to resemble the architecture of something alive. On the larger scales, the universe forms what scientists call the cosmic web. It is a vast network of filaments stretching across unimaginable distances, with dense knots where galaxy clusters gather and enormous empty voids between them. If you could step far enough away from everything and look back at the universe as a whole, it would not resemble a simple cloud of stars. It would resemble a structure, a network, a kind of hidden anatomy. This pattern had been predicted long before Webb, but Webb has made it feel more real. By detecting galaxies that earlier telescopes missed, especially those hidden behind dust or shifted into infrared light. It filled in missing threads. Places that once seemed thin or incomplete suddenly became dense with connections. The cosmic web did not merely sharpen. It became more populated, more textured, more persuasive. A helpful way to picture this is to imagine rainwater flowing across uneven land. It does not settle uniformly. It gathers into streams, then rivers, then larger channels, leaving other places dry and nearly untouched. In much the same way, matter in the universe flowed under gravity into certain pathways, draining away from other regions and creating a landscape of filaments and voids. Galaxies formed along those invisible routes, gathering where gravity was strongest. Some of the structures Webb has revealed are especially striking. Chains of galaxies extend for millions of light years, already organized when the universe was still comparatively young. In some cases, these galactic neighborhoods seem to have evolved with surprising speed. A few galaxies had already slowed or stopped forming stars, as though their environments had pushed them through their life cycles faster than expected. Even in the young cosmos, location mattered. To be born in a crowded region was to live under different conditions than a galaxy drifting in relative isolation. There is a strange beauty in this. The universe is not simply a collection of separate objects. It is relational. Galaxies influence one another. Matter flows along hidden routes. Vast empty regions and dense cosmic cities coexist in the same grand design. And Webb, by seeing farther and deeper, has helped us recognize that what once looked like scattered points of light is actually part of a much larger and more interconnected pattern. And yet, for all its richness, this visible web still belongs only to the part of the universe we can observe. Beyond our cosmic horizon, those same structures may continue indefinitely, threading through regions we will never see, which raises a quiet but unsettling question. If the universe is this immense and structured within our visible reach, how large is the part forever hidden from us? At first glance, the universe seems as though it should be easy to measure. The Big Bang happened about 13.8 billion years ago. Light travels at a fixed speed, so it feels natural to assume that the farthest thing we could possibly see should be around 13.8 billion light years away. For many people, even those with an interest in astronomy, that intuition still feels reasonable. And yet, it is profoundly wrong. The observable universe does not have a radius of 13.8 billion light years. It has a radius of about 46.5 billion light years, making its full diameter roughly 93 billion light years across. That number sounds almost impossible at first, because it appears to violate the very rule we began with. If light has only had 13.8 billion years to travel, how can the visible universe be so much larger? The answer lies in something our everyday minds are not built to imagine easily. Space itself expands. When we picture distant galaxies moving away from us, we often imagine an explosion, with matter racing outward into empty space. But that image is misleading. On cosmic scales, galaxies are not mostly flying through space like debris. They are being carried apart because the space between them is stretching. A better image is the surface of a balloon with dots drawn on it. As the balloon inflates, each dot moves farther away from every other dot, not because the dots themselves are crawling across the surface, but because the surface itself is growing. The universe behaves in much the same way. This means that when a very distant galaxy emitted the light we now detect, it was far closer to us than it is today. While that light was traveling through the cosmos, the space between us and the galaxy continued to expand. So the light was not crossing a fixed distance. It was crossing a distance that kept growing while it moved. In a sense, ancient light has been running on a cosmic treadmill. That is why Webb can detect light that has been traveling for more than 13 billion years from galaxies that are now tens of billions of light years farther away than where they started. The light began its journey when the universe was smaller. It reached us only because it left early enough, before expansion carried its source still farther into the deepening dark. This realization changes the emotional texture of the cosmos. The universe is not just large, it is dynamically large. It has been stretching beneath every photon in flight, quietly reshaping distance itself. And once you truly feel that, another unsettling truth follows close behind. If the observable universe is already 93 billion light-years wide, then whatever lies beyond it may be not just unreachable, but permanently inaccessible. There is no wall at the edge of the observable universe, no final barrier, no glowing border where reality simply stops. If you could somehow travel outward in any direction, you would not arrive at a cosmic cliff. Space would continue, galaxies would continue, structure would continue. The universe does not end where our sight ends, and that is precisely what makes it so unsettling. The observable universe is not the universe itself. It is only the region from which light has had enough time to reach us since the beginning of cosmic expansion. It is a horizon, not an edge. Beyond that horizon, countless galaxies may still exist, stars may still be forming and dying, black holes may still be merging, and entire histories may be unfolding in total isolation from us. Not because our telescopes are too weak, not because our technology is unfinished, but because space itself prevents the information from ever arriving. This is one of the most haunting consequences of cosmic expansion. In some regions, the distance between us and distant galaxies is increasing so quickly that light emitted there will never be able to overcome the stretching of space. It will never reach Earth, no matter how long we wait. Those places are not fictional. They are simply causally disconnected from us. Their existence can be inferred, but their details can never be known directly. This means that most of reality may be permanently hidden. And the strange thing is that every observer in the universe lives inside their own version of this limitation. If you were standing in some unimaginably distant galaxy, you would also see yourself at the center of an observable bubble, surrounded by a different set of visible galaxies and a different horizon beyond which everything disappears. There is no universal vantage point from which the whole cosmos can be seen at once. Every civilization, no matter how advanced, is trapped inside its own island of observability. That gives James Webb a strangely philosophical role. It is not simply extending our vision. It is carrying us right up to the edge of what vision can ever accomplish. Each time Webb detects a galaxy at extreme distance, it is not merely showing us something ancient. It is showing us something near the boundary of causal connection, a region so remote that its later story may never become visible to us at all. We do not see what is, we see what was, and even then, only a fraction of what ever existed. That is the quiet revelation hidden inside Webb's images. They are not just portraits of the deep universe. They are reminders of limitation. They show us that even at the height of our technological power, most of the cosmos remains forever beyond the reach of human sight. For much of the 20th century, astronomers believed the long-term story of the universe was fairly straightforward. The Big Bang had sent everything outward, and gravity, though perhaps slow, would gradually work to resist that expansion. The only real question seemed to be whether gravity would eventually slow the universe enough to halt its growth, or perhaps even reverse it one day. But in the late 1990s, that comforting picture broke apart. Astronomers studying distant stellar explosions called Type 1a supernovae noticed something deeply unsettling. These explosions are useful because they shine with a fairly consistent brightness, which allows scientists to estimate how far away they are. When those distances were compared to how fast their host galaxies were receding, the results pointed toward a shocking conclusion. The universe was not slowing down at all. It was speeding up. Something was causing space itself to expand faster and faster over time, not just continuing the original outward motion, but actively accelerating it. And because no known form of matter or radiation could explain this behavior, cosmology was forced to introduce a new and profoundly mysterious ingredient: dark energy. Dark energy is not a substance in the ordinary sense. It cannot be seen, touched, bottled, or directly measured in a laboratory. It does not form stars or clouds or galaxies. Its presence is known only through its effect on the universe as a whole. And yet, by current estimates, it makes up roughly 68% of everything that exists. Ordinary matter, everything visible and familiar, accounts for less than 5%. The stars, the planets, the oceans, the human body, all of it together is a minor ingredient in a cosmos dominated by things we cannot see. What makes dark energy especially strange is that it does not thin out the way normal matter does. If you double the size of a region of space, the same amount of matter is now spread more thinly. But dark energy seems to maintain a nearly constant density even as space expands, which means that as the universe grows larger, the total amount of dark energy grows with it. More space means more dark energy. More dark energy means faster expansion. Faster expansion creates still more space. It is a quiet feedback loop operating on the grandest scale imaginable. James Webb does not see dark energy directly, but it sees its consequences everywhere. The extreme redshifts of distant galaxies, the immense size of the observable universe, and the way ancient light has been stretched nearly beyond recognition, all reflect a cosmos shaped by this invisible force. Webb shows us not only what the universe contains, but what the universe has been doing while those photons were on their way to us. And what it has been doing for billions of years now is accelerating into greater separation. There is something almost tragic hidden in the story of cosmic expansion. The universe today is, in a sense, unusually generous to observers like us. We live at a time when the night sky still contains clues to its own origin. We can still detect distant galaxies. We can still see the cosmic microwave background, the ancient afterglow of the Big Bang. We can still reconstruct a meaningful history of how everything came to be. But this may not always be true. If dark energy continues behaving the way current observations suggest, then expansion will go on accelerating indefinitely. Over immense spans of time, more and more galaxies will be carried beyond our cosmic horizon. Their light will become increasingly redshifted, stretched into longer and weaker wavelengths until it fades beyond detectability. From our perspective, those galaxies will not explode or vanish dramatically. They will simply dim, freeze in time, and quietly disappear. In roughly 100 to 150 billion years, future observers in our local region of space may look outward and see almost nothing beyond their own gravitationally bound group of galaxies. The vast cosmic web, the distant clusters, the great evidence of expansion itself may all be gone from view. They might live in a universe that appears small, static, and strangely empty, and they may never know otherwise. This is one of the most haunting implications of modern cosmology. There may come a time when the true scale and history of the universe can no longer be discovered from within it. Future civilizations, no matter how intelligent, may have less evidence available to them than we do now. They may never know there was once a visible cosmic horizon filled with galaxies, or that the universe had a beginning at all. James Webb makes this realization feel sharper. By pushing our vision closer to the deepest observable past, it reminds us that we are living in a rare and temporary window of cosmic visibility. We are late enough in the story for stars, planets, and life to exist, but early enough that much of the universe is still accessible to observation. That is a remarkable privilege, and it adds a strange emotional layer to astronomy. We are not only exploring the cosmos, we are witnessing it during one of the few eras in which its wider truth can still be seen, which makes the universe feel not just vast, but fleeting in a way that is difficult to forget. If dark energy explains why the universe expands faster and faster, then something else must explain why matter does not simply drift apart into featureless fog. Galaxies exist. Clusters exist. Vast filaments stretch across the cosmos. Stars gather into rotating systems rather than scattering into emptiness. Something is holding structure together. That something is dark matter. Like dark energy, dark matter is invisible. It does not emit light, absorb light, or reflect light. No telescope can photograph it directly. And yet, its gravitational influence is written everywhere across the universe. By current estimates, dark matter makes up about 85% of all matter that exists. Everything we can actually see, every star, planet, nebula, and glowing galaxy, is built inside a much larger invisible framework. The first clues came when astronomers studied how galaxies rotate. According to the gravity produced by visible stars and gas alone, the outer edges of galaxies should orbit more slowly than the inner regions, much like planets in the solar system. But that is not what the universe does. Stars far from galactic centers move much faster than they should, as though each galaxy were wrapped inside a huge unseen halo of mass. The same pattern appears on even larger scales. Entire clusters of galaxies behave as though they contain far more matter than we can account for. Light from distant background galaxies bends around these clusters more strongly than visible matter alone can explain. Again and again, the conclusion returns. Most of the universe's matter is present, but hidden. What makes dark matter especially important is not just how much of it exists, but how early it began to shape the cosmos. Ordinary matter in the early universe was hot, energetic, and slow to collapse. Dark matter, however, could begin gathering under gravity far sooner. It quietly formed invisible halos and structures long before the first stars ever ignited. Then, as the universe cooled, ordinary matter fell into those gravitational wells, collecting into the regions where galaxies would eventually form. In that sense, dark matter built the scaffolding of the visible universe before the visible universe even existed. James Webb has made this picture feel more vivid than ever. By detecting galaxies at astonishingly early times, Webb shows that visible matter alone could not have assembled the cosmos so quickly. Something had to provide the gravitational head start. Something had to gather mass before the stars began to shine. And all evidence still points to the same invisible architect. Once you begin to understand dark matter, the large-scale structure of the universe starts to look less like a random scatter of galaxies and more like a hidden design gradually made visible. Galaxies do not simply appear anywhere. They gather along routes, cluster at intersections, and avoid certain vast regions almost entirely. What James Webb helps reveal is that the luminous universe follows an invisible skeleton. That skeleton is the cosmic web. On the largest scales, dark matter appears to be arranged in immense filaments stretching across tens or even hundreds of millions of light years. These filaments intersect in dense nodes where galaxy clusters grow, while between them lie cosmic voids, enormous regions so empty that they contain almost no galaxies at all. The visible universe traces this structure like frost outlining a hidden pattern on glass. For decades, much of this picture came from simulations and indirect evidence. Astronomers could infer the web from the distribution of galaxies and from how gravity should shape matter over time. But more recently, observations have begun to catch glimpses of the web's dark backbone more directly, especially through gravitational lensing, where invisible mass subtly bends the light of more distant objects. Webb strengthens this picture by showing how early and how richly these structures already existed. Filaments and galaxy groups were forming surprisingly soon after the Big Bang. Matter was already flowing into denser regions, feeding star formation and helping build the first substantial galaxies. The early universe was not an aimless cloud. It was already organizing itself along hidden lines of gravity. This also means galaxies are not isolated islands in any simple sense. They are connected to a much larger environment. Gas can stream along filaments like water through channels, feeding galactic growth over vast timescales. Galaxies born in crowded regions evolve differently than those in solitude. Some grow rapidly and burn through their gas early. Others remain active for much longer. Even on cosmic scales, location matters. There is something quietly beautiful in this idea. The universe is not just a collection of things. It is a structure of relationships. The stars we see are only the illuminated surfaces of deeper forces. The glowing galaxies are not floating freely in darkness, but suspended within a framework almost entirely invisible. And that realization brings us to perhaps the strangest perspective of all. If most of the matter is invisible, if most of the energy is invisible, and if most of the universe lies beyond our horizon, then what we call reality may be only the thin lit surface of something far larger than we were ever meant to see. By the time we reach the edge of what James Webb has revealed, something quietly unsettling begins to settle in. The universe no longer feels like a collection of stars and galaxies floating through empty space. It feels layered, partial, hidden, as if everything visible is only the illuminated skin of a far deeper reality. Consider what Webb has forced us to accept. The earliest galaxies appeared sooner than expected. Supermassive black holes seem to have grown before they should have had time. The observable universe is vastly larger than our instincts allow. The number of galaxies may reach into the trillions. Most matter is invisible. Most energy is invisible. And beyond our cosmic horizon, the greater part of existence may remain forever inaccessible. That is not a small revision to our worldview. It is a transformation of it. For centuries, science has often been described as the process of bringing light into darkness, of replacing myth with clarity and uncertainty with understanding. And in many ways, that is true. James Webb is one of the greatest instruments of that effort ever built. It has extended human sight deeper into space and farther into time than any machine before it. It has shown us galaxies from cosmic dawn, hidden structures in dusty regions, and light that began its journey before our solar system existed. And yet, strangely, the deeper Webb looks, the more it reminds us of how little we truly command. Because every discovery it makes also sharpens the outline of what remains hidden. It shows us the observable universe, but in doing so reveals how much lies beyond it. It shows us galaxies, but forces us to acknowledge the invisible dark matter holding them together. It shows us ancient light, but points toward dark energy pulling everything farther apart. It shows us structure, but also reminds us that what we call everything may be only a local fragment of a far greater whole. There is something almost historical about that realization. Human beings have always lived at the boundary between knowledge and mystery. Medieval mapmakers drew the edges of the known world and filled the blank spaces with dragons and speculation. We smile at that now, but in truth, we have done something very similar with the cosmos. We have mapped what we can reach, named what we can measure, and beyond that horizon lies a vast unknown, still untouched by certainty. James Webb has not removed that mystery. It has made it more precise. And perhaps that is the most honest gift science can offer. Not the illusion that reality is now fully understood, but the deeper and more beautiful understanding that the universe remains larger, stranger, and more hidden than we imagined. And with that, we come gently to the end of tonight's journey. From ancient light crossing billions of years, to galaxies forming too soon, to invisible matter shaping the great cosmic web, the James Webb Space Telescope has shown us that the universe is not just vast. It is profoundly mysterious, layered with histories and hidden structures that stretch far beyond the reach of human life and human sight. And perhaps that is what makes it so calming to think about at night. The quiet reminder that beyond all the noise of daily life, there is a universe so immense and so ancient that it humbles every worry into perspective. If you enjoyed tonight's story and you'd like more long, peaceful journeys through history, mystery, and the deeper edges of the world, then make sure to subscribe to The Sleeping Historian. And if you'd like, leave a comment letting me know where in the world you're listening from tonight. Until next time, rest well and drift gently into the dark.